Hello, everyone. Welcome to Beyond IID. Um, I think we should simply start with our first speaker. Our first speaker is Ian George, and the title of the talk is The Communication Value of a Quantum Channel. Ian George, the floor is yours. Could I please ask you to share your screen? And yeah,
Am I unmuted? Can people hear me?
yes, you are heard.
Okay, thank you so much. Well, let me go. There we go. Okay, and everyone can see the screen?
Yes.
Great, thank you so much. Hello, I'm Ian George. Thank you to the organizers for having me. I'm going to be presenting joint work with Eric Chitambar, Brian Doolittle, and Marius Junge on the communication value of a quantum channel. So if we can consider the following sort of simple setup, Alice and Bob share some classical channel with input space X to output space Y, and Alice would like to send messages over it, but the messages she's going to send are equiprobable. And so Bob would like to decode these messages, and in this simple scenario, we know that the best thing he can do is maximum likelihood decoding. So he looks at what output he gets, and then he just says what's the most probable input that would lead to this, and he picks that, and then the probability of success normalizes over the input space. So what we decide to do is we say, well, we're not really interested in the normalization, so we define the communication value of a classical channel as just the maximization part. And so we can see that maybe this might be an interesting quantity in the sense that it seems to be a measure of noise. So if the channel preserves every input, then the communication value is the dimension of the input space. And if it maps every input to a uniform distribution over the output space, then the communication value is 1. So it seems to have some notion of noise. And so the natural question is then, okay, how does this work for quantum channels? And so it's the normal way that you consider classical communication over quantum channels, where you have some encoder, and then you run it through your quantum channel, and then you decode it on the output, and that induces a classical channel. And then we would say that the communication value for a quantum channel is just the supremum over communication values for all induced classical channels. One thing that's important to note here, though, is we threw out the normalization. So this isn't exactly a coding problem. In some sense, you might want to think of it more as a game. And in some sense, there's this other aspect that it seems likely that it would be helpful to drive up the number of messages you send to achieve this value more than if you were considering a coding problem. So now that we know what the communication value is for a quantum channel, let's motivate the rest of the talk. So the first thing we can do is we can show the communication value admits a conic program on the choice state. The next thing we can do is we can show that this conic program can be sort of seen as a function of the separable min entropy, which we'll define in a bit. And then we can also show that the communication value is proportional to the Max-Holevo quantity. And so we see that we're sort of in this classical capacity notion, but not exactly. Furthermore, we can show that it's non-multiplicative for some channels, which we know is always an interesting property in quantum information theory. But we can also see that it's multiplicative if one of the channels is entanglement breaking. So we can see whatever's making it non-multiplicative is a special property of being able to preserve entanglement with your channel. Lastly, we can show that it's multiplicative if both channels are qubit channels. So there's something about dimension at play in this. And then we can also show operationally that it has something to do with classical communication for zero error simulation of any classical channel induced by the quantum channel, either in terms of using a classical non-signaling resource or a quantum non-signaling resource. So we can see that it has a lot of properties that are interesting. So let's just jump into it. So the first thing we do is we sort of relate it to minimal error discrimination. So the image that I showed earlier is you have your uniform input, you have your encoder, you have your decoder, but then you have some output space Y, and it's not clear what that should be. But you're able to show that, in fact, it's always achieved by picking that the output space is the same as the input space. And so it looks like it's basically minimal error discrimination. There is the caveat that, again, these are not conditional states. These are fully normalized quantum states because we're not really thinking of a probability of success. And the reason I've said that we can restrict the input space to be the output space squared is of the channel is because you can use an extremal POVM, which means we have sort of a final a finite thing to optimize over, so we don't need the supremum, we can have a maximum. And so then using that, the next thing to do is I promised a conic program. So we take this sort of minimum error discrimination problem, and we can just use the action of the choice state in terms of the action of the channel to get it into this form. And then you'll notice that if you were to trace off over the quantum states, you'd get the sum over a POVM, and so that's the identity. And so we get the communication value of a quantum channel is this conic program, and that's sort of straightforward. And the best thing to do whenever you have a primal problem is to write down the dual problem. So you look at this, and if you're sort of used to these things, you say, oh, well, of course, this looks exactly like the SDP for the min entropy, except for that we're now considering the separable cone instead of the positive cone. So now maybe we should look at this in terms of in entropic terms. So that's what we do. So just to recall, the max relative entropy is this optimization program where this is the loner ordering on the positive semi-definite cone. And so the min entropy can be defined in terms of the max relative entropy, and then the SDP is given in this form. And so we're just doing the whole same thing, but we're going to use the dual cone for the separable cone, the dual of the separable cone. And so we have a separable min entropy that's defined in terms of a separable max relative entropy. And that gets us the dual problem for the CV that we showed. And so we have the communication value equals the exponential of the negative of the separable min entropy. So since we have it in terms of this entropic quantity, then this helps in various ways. So one thing is we can consider data processing. So physically, it's sort of straightforward to think about data processing because, of course, if you had some pre-processing and post-processing on your quantum channel, you could always just absorb that into your encoder and decoder. And so you expect that the communication value can only decrease under pre and post processing. But formally, this comes from a data processing on the separable min entropy. And in fact, it's the same as the one you can get for the standard min entropy, though actually we can strengthen this for a more general class of maps. I just stated here in the way that it looks the same as for the normal min entropy. Okay, so now we see that it's useful in that fashion to look at the min entropy. So the next thing to look at would be how we relate this to the Max-Holevo. This is the only proof I sort of show, but the advantage is here we see a bunch of operational interpretations just sort of in a sequence. So we start with the dual problem for the communication value, and then we can convert this into this form where what we've done is we've used the way that you can convert the dual cone for the separable the dual separable cone into positive semi-definite constraints, and then the definition of the action of the choy. And so this is sort of interesting because what we have here is we're seeing that the communication value basically captures some notion of the image of the channel. And then the next thing we can do with that is we can convert it basically into a classical quantum state, but we have to get rid of the regularization. And so we get it in terms of the min entropy on the induced classical quantum state where you're using encoding on the quantum channel. And so from there, what we do, okay. So then the min entropy, as we showed earlier, is defined in terms of the max relative entropy. And the nice thing about the max relative entropy is effectively it gets rid of the information about the prior probability on the input messages. And so you can actually convert it into being an optimization over arbitrary classical quantum input states. And so you get the Max-Holevo. One thing to note about this, though, is that Junge in his PhD thesis already defined this term, and he called it the operator radius of n, and he showed that that was proportional to the exponential of the Max-Holevo. However, his definition doesn't go through this min-entropy part in the middle. So that's something that's helpful for us at least. And then another thing to note is that it's sort of intuitive that you get this result by Koenig et al., because in that work, they show that the exponential of the min entropy on a classical quantum state is the maximal probability of guessing what the classical data is from the quantum side information. And so we can say like, okay, well, what we showed in the previous slide is that the CV is equivalent to considering this sort of mapping, but what the min entropy is really telling you is the optimal decoder. And so it's equivalent basically to the original definition once we realize that it has something to do with the minimal error discrimination. Another thing about using the min entropy approach is then we get an extra operational interpretation where effectively what we can see is that the communication value evaluates the recoverable singlet fraction, where you can only use an entanglement breaking channel to do the recovery. So of course, this is sort of strange because if you use an entanglement breaking channel, you're not really going to get a good singlet fraction, but it does have some sort of notion of classical communication in this framework. And the other advantage of this is when we relax the cone from the separable cone to the PPT cone, then we sort of recover this operational interpretation again. Okay, so as I said before, like we don't really think it's a coding measure per se, but it seems to be a measure on the states, and it has something to do with preserving entanglement. So maybe it would be good to look at it in terms of entanglement measures. So if you consider the geometric measure of entanglement, you can see that this is just basically the closest product state to the Choi state up to the normalization of the Choi operator. And you can rewrite this in this optimization form. And what you see here is that it's very similar to the communication value, except for you only get a single input and a single measurement. And in fact, that's why Werner and Holevo have previously shown that this is equivalent to the maximal output purity. And so what we show is that you can see the communication value should basically be bounded between the geometric measure of entanglement on the Choi state and that scaled by the output dimension. And in fact, we can show that it's not equal to either of those in general. So it's sort of its own distinct measure, as one might expect. So we know that entanglement measures are non-multiplicative sometimes. So the natural question would be, can we make the communication value non-multiplicative? And indeed we can, and we can do it using entanglement measures. So we can consider this channel given by this Choi state. For those who are more comfortable, this operator is equivalent to the projector onto the antisymmetric subspace. And Zhu et al. Have shown that the geometric measure of entanglement for a single copy is given by this expression. But if you consider two copies of this operator, then it's given by this expression. And the nice thing about this is the maximizations in both of these cases are full bases. So you could do this d times. And in fact, in the two copy case, the optimizers are the Bell entangled states, or maximally entangled states, the Bell states. And so using this, we can get that the communication value for the single copy is d over d minus 1, but in the two copy, it's 2d over d minus 1. And so for d greater than or equal to 3, the communication value is non-multiplicative. So that's cool. So we know there's something interesting going on there. And then the question would be, if we know when it's that it can be non-multiplicative, when can we guarantee it is multiplicative? So these are possibly non-exhaustive, but these are interesting cases. So if one of the channels is entanglement breaking, then it's always multiplicative. And this is cool because this tells us that this measure being non-multiplicative really has something to do with preserving entanglement. And if both of them are qubit channels, then it's multiplicative. So there's something about dimension. And then we have this result about if both channels are covariant with respect to groups that are irreducible unitary representations on the full space, and one of them is component-wise non-negative for their Choi, then you have multiplicativity. And this component-wise non-negative is really important because otherwise the previous example we gave would satisfy these conditions. So there's something interesting going on there. So we can look at sort of the proof for entanglement breaking being multiplicative just pictorially, which is nice. So of course we consider you have an entanglement breaking channel and you have an arbitrary channel, but you could redraw it in this fashion, right? And so you have this output for the entanglement breaking channel, and then you have some conditional state on the input. But we already mentioned that the communication value effectively measures the image of the channels. And so you can see that there's really no way this could increase the image by running it in parallel, because you could have just put row A through the entanglement breaking channel and get the same image. And for whatever conditional state, you could have run it through the original channel and gotten the same image. So there's nothing really going on there. So that's one intuitive way of looking at this. Then for qubit channels, I'm not going to go through the through the multiplicative result, but for a single copy, it's sort of interesting because you can see that the communication value is 1 plus the maximum singular value of the correlation matrix for that qubit channel. And so physically, this is sort of intuitive because the singular maximum singular value tells you basically what pure state will get mapped to the most pure state. And what this theorem is saying is you should take that state, its antipode, run them through the channel, and then project onto the maximally pure state. And this happens to be the optimal. So it's sort of like what you would guess, but it's nice that it works out. And then it being multiplicative follows from being able to construct something that guarantees that multiplying two channels with this communication value will satisfy. But it's important to note that it really relies on the structure of how two qubit channels in parallel run. So it's not clear how this would generalize in any fashion. And so then now we've looked at places where it's multiplicative and where it's not multiplicative. Maybe we can do something interesting if we give an extra resource. So we consider an entanglement-assisted communication value. And so in this case, you have some maximally entangled state in some space, and Alice is going to use half of it to encode based on her input, and the other half goes to Bob, and then Bob gets to decode on both. And the theorem is, in this setting, the entanglement-assisted CV, which we call CV star, is given by the exponential of the negative of the min entropy of the choice state. And so here we see that somehow the entanglement-assisted case has gone from the separable min entropy to the standard min entropy. And another thing that's interesting about this is we know that the SDP for min entropy is multiplicative. And so we have this sort of parallel between the way classical capacity of a quantum channel is not in general multiplicative, but entanglement assisted is. And so there are these nice parallels going on there. And another thing that's interesting to note in this case is that the achievability is done effectively using superdense coding on a DA dimensional EDIT. So that's cool. So, I mean, we just saw that it had, if you have one resource, you have the min entropy, and originally we had the separable min entropy. So it might be natural to say, like, okay, let's just define the communication value for an arbitrary conic cone, and then in terms of this like cone K min entropy on the choice state. And then you have the same sort of primal problem just over a different cone. And so of course the natural choices of cone would be separable, which would get you CV, positive, which would get you entanglement CV, PPT, which would get you, I mean, not a direct thing, but you can see that it's the like SDP relaxation of the original communication value, and then the K-symmetric extension cone, which would be the way to interpolate between separable and PPT. And one thing we have that's interesting here is that if you have two copositive maps, which is to say their choice states are PPT, then the communication value PPT will be multiplicative. And so that's kind of cool because it mirrors the entanglement breaking for the separable cone. But an open problem that might be possible is to consider two channels that are copositive and whether or not the communication value should be multiplicative still. And so this would be sort of like a bound entanglement problem, but on choice states. And I'll show an example that might suggest this could be true. Of course, we have no idea if it is, but I think it's an interesting problem. So we consider the Werner-Holevo channels, and the Werner-Holevo channels are a generalization of the non-multiplicative result we saw earlier. You just set lambda equal to 0 to recover the previous result. So we would like to see how far it goes. And so, since these channels are UU covariant, the CVPPT can be written as a linear program, so we can consider multiple copies much easier. And then the space of separable UU-VV invariant operators is the same as the PPT space. And so that was proven by Volbrecht and Werner. But so that means if we consider two Werner-Holevo channels ran in parallel, we can get the CVPPT to equal the CV for sure. And so what we see is we have this whole regime where it's not multiplicative. The blue line is for two copies of the Werner-Holevo channel. For higher numbers of copies, we only know that we have the CVPPT. But what's interesting here is that all of the non-multiplicativity dies out at 0.3 for the channel parameter, but we know that these channels are not entanglement breaking, but also not co-positive until 0.5. And so there seems to be some much stronger condition for the non-multiplicativity to arise. And then we can also instead of looking at the non-multiplicativity directly, we can just look at the CVPPT directly as a curve. And so of course you see this truncation at 0.3 where it changes, and you can see where it becomes the maximally depolarizing state. So it's kind of interesting. Another thing we can do by considering the CVPPT is by the previous covariance result we showed earlier, we know that the Werner-Holevo channel with any ancillary identity channel will be multiplicative, but we find this is not true if you go to the CVPPT cone. And in fact, it seems like it's sort of unbounded, like if you just keep giving it a larger identity channel running in parallel, you can really blow up the difference between CVPPT and CV. So this shows a sort of a strong gap. And it also implies that there are PPT entangled states in the UU-VV bar operator space, which is different from what we showed earlier with the UU-VV by Volbert and Werner. So the next question would be like, as we really motivated this in terms of classical information, but we know that there are places where coherent information can be non-additive. So we'd like to know if these are sort of really distinct cases in our setting. And so we consider the D. Fraser channel and we consider the CDU channel. And both of these are known to have super additive coherent information. For the D. Fraser channel, it's for a specific regime. For the CDU channel, it's most of the regime, or it might actually be all of the regime. But for us, the multiplicative communication value holds for the entire regime. So there's this clear separation between classical and coherent information if we view the communication value directly as being in terms of classical information, which it seems like we should from the motivation. Lastly, we want to consider the relationship between channel capacity and simulation, because I said we were going to do that. And another reason it's very interesting is part of the motivation for this was that the communication value is in fact a facet on the channel non-signaling polytope. This was shown by Doolittle and Chitambar earlier last year. And so certain ways we can tie this together from previous results, the classical no signaling one-shot zero error classical simulation cost of a classical channel is given by the communication value of the classical channel. It was not stated in terms of communication value there, but that is in fact what the measure is. And then this was extended by Dwan and Winter to the quantum no signaling one-shot zero error classical simulation. And that is encapsulated by the entanglement-assisted communication value. And then previously it had been observed by Cubbett et al. That the capacity could be bounded by the logarithm of the communication value for a classical channel. And so we can actually generalize this using our interpretation of our relationship between communication value and Max-Levo information to get it for the classical capacity of a quantum channel and also for the entanglement-assisted quantum channel capacity, the classical capacity. So to summarize, we introduced the communication value and we went through a bunch of its properties and why they're interesting. So it admits a conic program. It seems to motivate this new restricted min entropy, the separable min entropy. It's proportional to the Max-Levo quantity. Both channels must preserve entanglement for non-multiplicativity to work or to happen. So it seems to be very important about entanglement. It's multiplicative for any two qubit to qubit channels. So there's something about dimension going on. We introduced the entanglement-assisted CV, which is achievable by super dense coding, and also it's always multiplicative. So we have the same sort of gap as in classical capacity and entanglement-assisted classical capacity. And then we introduced these sort of general conic communication value and min entropies and some practical use for them for talking about the communication value. And lastly, we looked at the relationship between communication value, non-signaling assisted channel simulation, and classical channel capacities. So thank you.
Thank you, Ian, for your talk. I don't see any questions on the Slack channel. So at this point, I would like to ask the participants to, if they have any questions, to directly unmute themselves and ask. Any questions?
Sorry, I have one question.
Sure, please go ahead.
So I understand that the combination quantity is somehow very interesting, but combination value. I could not find the rigorous definition of communication value of quantum channel.
Sorry, I think
I could not. Could you show me the rigorous definition? So you mentioned that somehow that is related to the encoder and decoder, so somehow related to the classical capacity, but maybe this one is not classical capacity. So I want to understand the difference from the classical capacity of quantum channel.
so this is not the classical capacity. I was mostly just trying to draw parallels between things we are used to seeing in classical capacity in terms of like non-additivity and inducing a classical channel via an encoder and a decoder.
So I cannot understand what is the CV of that classical channel. So in that your definition, you employ CV for classical channel.
Mhm.
So
Sorry, I'm not sure I'm fully understanding the question.
yes, my question is this one is you consider the CV P epsilon CV EDXY. So that P is classical channel. Okay.
Mhm.
So in that definition, you use CV for classical channel. So I cannot understand that definition CV for classical channel.
So the
Here.
yeah, sorry. Let me bring it up so it's not overlapping. So this is the CV for a classical channel.
This one. So CVP. You consider that maximum value. Oh, I see. Okay. For each X. Oh, okay, I understand.
Okay. Sorry about that.
Right. So actually, I do see some more questions, but because we need to continue, so I would request people to go to the Slack channel, which I have put on the chat, and I believe that Ian George could perhaps answer the questions over there. Or right, we need to move on to the next talk. Thank you very much.